This is Offscreen Works. We look at ordinary things and show the systems quietly doing the work behind them. Today, why damaged QR codes can still scan. This QR code is damaged. The center is partly covered, some modules are missing, and there is noise around the symbol, and your phone may still read it. That can look like the camera is guessing the missing picture, but a QR scanner is not guessing. A QR code is built as a data system for an imperfect world. The useful way to understand a QR scan is as a pipeline. First, the phone captures a messy camera image. Then it finds the QR symbol, corrects the perspective, turns the image into a clean grid, reads groups of bits called codewords, and only then repairs some of the damaged codewords. So the question is not, can the phone recognize the picture? The question is, can it recover enough structured data from the grid? The first landmarks are the three large squares in the corners. They are called finder patterns. They tell the scanner where the QR code is, how large it is, and how it is rotated. Once the scanner has those landmarks, it can flatten a tilted camera view into a square grid. This is why a QR code can be scanned from an angle, but it also explains one of the weak points. If a finder pattern is badly damaged, the scanner may never reach the repair step. The quiet zone is the empty border around the QR code. It looks like unused space, but it is part of the symbol. The scanner needs it to separate the code from the background. If a QR code is printed edge to edge on a busy design, the phone may not know where the code starts and the background ends. The data may still be there, but the scanner can fail before it reads it. After the symbol is found, the scanner samples it as a grid. The small black and white squares are modules. The camera image is not perfect. It has blur, shadows, perspective, and compression. So the scanner has to decide, is this cell dark or light? That decision creates a stream of bits, but one module is not one letter. The message is spread through many bits, mixed with service information and error correction information. Some parts of a QR code are not the message itself. They are instructions for decoding the symbol. Format information tells the scanner things like the error correction level and which mask pattern was used. The mask is a deliberate pattern applied to the data so the final QR does not contain visual patterns that are hard to scan. The scanner reads this service information, removes the mask, and only then interprets the data. That is why damaging a small service area can matter more than damaging the same number of ordinary modules. The bits are grouped into codewords. A codeword is usually shown as a small 8-bit chunk. Some codewords carry the message. Other codewords carry error correction information. You can think of those correction codewords as mathematical backup. This is the important shift. QR error correction does not repair pixels. It repairs codewords after the scanner has already converted the picture into a grid of bits. QR codes use Reed-Solomon error correction. In simple terms, the symbol stores enough mathematical backup to rebuild part of the missing or wrong code words. There are 4 common correction levels, L, M, Q, and H. Roughly, they can restore about 7, 15, 25, or 30% of damaged code words. But that does not mean you can erase any 30% of the visible image. The location matters. The scanner must still find the symbol, read the service information, align the grid, and keep the number of damaged code words within the correction capacity. There is one more reason local damage can be surprisingly survivable. QR codes do not simply place all related bytes in one neat block on the image. Data and correction code words are distributed through the symbol. That means a scratch across one visual area may become smaller errors spread across several correction blocks, instead of one fatal hole in a single block. This is a simplified view, but it explains why a local mark in the center can sometimes be repaired. This is why the correction level matters in real QR design. The same payload can be encoded with L, M, Q, or H correction. Higher correction stores more backup, often making the symbol denser or larger, but giving it more ability to survive dirt, print defects, or a logo. The right level is not always H. For tiny prints, dense codes can become harder to scan. For logos or outdoor use, higher correction is usually safer. The final answer is always a real scan test. A logo QR code works only because the logo is controlled damage. The creator usually uses a high correction level, keeps the finder patterns and quiet zone clear, and places the logo where the symbol can afford to lose information. If the logo is too large, too close to a corner, or the print quality is poor, there is no magic. The code simply stops scanning. Not all damage is equal. A center mark may work. A damaged finder pattern can stop detection. A broken quiet zone can blend the code into the background. Low contrast, blur, glare, or a tiny printed size can turn modules into uncertain gray cells. So do not judge a QR code by the percent of visible area that is missing. Judge it by which functions are damaged: detection, separation, grid sampling, service information, or data repair. The practical rule is simple. Keep the 3 large corners clear. Leave the quiet zone. Use higher correction when you add a logo or expect damage. Keep enough physical size and contrast. And always test the final code with a real phone. A QR code does not guess the missing picture. It survives because its data was structured to be found, sampled, and partly repaired. If you like seeing the quiet systems behind everyday objects, subscribe to Offscreen Works. Next time, we will open up another ordinary thing and show what has been working in the background the whole time.